let's take aldehydes especially that we already have and look at how we oxidize them. We can oxidize the aldehydes all the way up to the carboxylic acid level, and that's because there's a hydrogen attached to the carbonyl. We have to remove a hydrogen from the carbonyl carbon if we want to oxidize it any further. So replacing that hydrogen with a CO bond, OH, for instance, there makes a carboxylic acid. That's why ketones cannot be oxidized. There's no hydrogens to remove, so there's no more CO bonds that can be made on there. So under normal conditions, ketones cannot be usefully oxidized. If I have an aldehyde, I do need to use a powerful oxidizing agent like CrO3, right? Chromium trioxide, chromium 6 oxide, in order to oxidize it all the way up to the carboxylic acid. So hexanal becomes hexanoic acid with CrO3. We can just quickly summarize our oxidation and reduction reactions, starting with primary alcohols. If I just have one propanol, 1, 2, 3, that can be oxidized gently with PCC to make an aldehyde. That can be oxidized all the way with CrO3 to the carboxylic acid. Going in reverse, the carboxylic acid can be partially reduced with dibol, diisobutyl aluminum hydride. The aldehyde can be reduced to the alcohol with any old reducing agent. Sodium borohydride is the safest. Of course, if I use a harsh reducing agent on the carboxylic acid like lithium aluminum hydride, I can take it all the way down to the alcohol. Starting with a secondary alcohol like 2-butanol right there, I can use PCC, oxidize that to 2-butanone. That can be reduced with sodium borohydride to get us back to the alcohol. Tertiary alcohols like let's just do t-butanol. Cannot be oxidized. No room for any more CO bonds on that compound, right? So be very familiar with these reactions. It can be a major part of organic synthesis, just because alcohols and carbonyl compounds are such useful synthetic points to have. They give you access to every other functional group.